Here I am going to explain about transient response analysis. Transient response analysis. This concept mainly have four parts. That is, first one is introduction. Second one is transient response analysis of RL circuit. Third one is transient response analysis of RC circuit. Fourth one is transient response analysis of RLC circuit. So these four parts we are going to study in this transient response analysis. So let me explain first what is meant by let me explain the introduction here. Introduction. Introduction to this transient response analysis. So to understand this transient response analysis, we should understand what is meant by transient response. To understand this transient response, let me explain about the system first. So this is a system. It is a system. System is nothing but a group of elements connected in such a manner that whenever we are giving the input for the system, it produces the output. This output is also called as a response. This response may have both transient response and steady state responses. Let me explain with an example of a fan. See here, this is a fan. Which was connected with an electrical supply through a switch. So this is the phase and neutral. It is the phase. This is the neutral. This is an AC input, and this is the switch. These are the wires connects this electrical voltage to an electrical input to this fan. Okay, now this system here is this fan. These are the group of elements. System is nothing but a group of elements. These elements are this fan, wire, and this switch makes a system here, and the input here is electrical voltage. So here the input is electrical voltage. And the output here is mechanical speed. The input is electrical, output is mechanical. So this is an input and this is the output. So system is nothing but a group of elements connected in such a manner that whenever we are giving the input for the system, it produces the output. Okay. Now if you switch on the fan, what happens? This fan will rotate. So during the initial period, what will happen? Suppose let us assume the full speed of the fan is 1000 rpm. The full speed of the fan is 1000 rpm. Okay. Whenever we switch on the fan, will it rotate with its full speed? No, it doesn't rotate with its full speed. Slowly it is trying to reach its full speed 1000 rpm. That means if we draw the graph between the speed versus the time, t is equal to 0, this is the time here, 1 second, 2 seconds, 3 seconds, 15, 20 seconds, 13 seconds, 30 seconds, like that. In x-axis I am taking the time as parameter, in y-axis speed is the parameter of the fan. Whenever I switch on the fan at t is equal to 0, it is trying to rotate. Initially the speed at t is equal to 0, the initial speed is 0, and the maximum speed here is 1000 rpm. Let us take this is the 1000 rpm speed, 1000 rpm, where rpm means rotations per minute. And whenever we switch on the supply, this fan will picks up its speed slowly and trying to reach with its full speed. So this is the graph of a speed versus time. Now this time, this one, this part, this is having, the speed is having the two parts. It is one part, it is another part here. And I want to say here another point here is the speed of the fan will depends upon the current. That means the speed of the fan is proportional to the current flowing through the this fan. So N or current I of t also, I current flowing through this fan. Alright, here in this curve it is having the two curves. It is one curve and is another curve, and this part is called as, this part of response is called as transient response. Transient response. This part is called as steady state response. Steady state response. Okay. And the period during which the transient response is existing is nothing but transient period. Transient period. This is called as steady state period. Steady state period. Okay. So here in this transient response analysis, we are going to analyze the response of the system during this period, during the transient period. That means we are going to analyze this transient response only in this unit. Okay. So transient response is the response of a system which will exist during the initial period after the switching action is done. Anyway, after some time it reaches to its steady state and this transient response will die out. And the time, normally it takes 5 tau time constant time to complete the transient response, where tau is the time constant. I will explain what is meant by time constant in later on classes. Okay, so here this is the transient response, it is the steady state response. So in this introduction concept, what I want to explain here is what is mean by, first one is what is mean by transient response analysis. Sorry, what is meant by transient response or transients? What are the transients? Second one is the reason behind the production of transients. The reason behind the production of the transients. Third one is how to analyze the transients. How to analyze the transients. These three concepts I am going to explain in this introduction concept. So the transients, or what is meant by transient response, just now I explained here with a practical example. Transient response. Okay. it is a response which will exist during the initial period after switching action is done. Next, the reason behind the production of the transients here. See, before going to explain what are the reasons behind the production of these transients, let me explain the time scale here. The time scale. See here, the time scale is, let us take, it is a time scale. It is 0, 0 minus, 0 plus, it is tau, 5 tau, it is infinity, it is minus infinity. This is nothing but the time scale. In this time scale, t is equal to 0, this point, this is the time axis, t is equal to 0 is the instant at which the switching action is done. The switching action is done. So it is an instant. Suppose if I take this circuit here, t is equal to 0, it is an instant at which the switching action is done. Now t is equal to 0 minus, it is the instant just before the switching action is done. Just before the switching action is done. T is equal to 0 plus is the instant just after the switching action is done. Just after the switching action is done. Just before or immediately before the switching action is done. Just after or immediately after the switching action is done. So t is equal to 0 minus, t is equal to 0 plus, t is equal to 0. And t is equal to tau, where tau is the time constant. Tau, t is equal to tau is the one time constant. Time constant. What is meant by time constant? I will explain in later classes. T is equal to 5 tau. It is the normally it is the time taken by the transient response. That means time to complete the transient response, or it is nothing but the transient period. It is transient period. Okay. So to analyze this transient response analysis, we should understand this time scale. T is equal to 0, 0 minus, 0 plus, tau, 5 tau. And t is equal to infinity is final stage. It is final or final stage. It is okay. Now let me explain the reason behind the transients. What is meant by transients is over. Transient response is over. The reason behind the production of the transients. The reasons are either due to the sudden changes in the sources or sudden changes in the circuit elements. Reasons are either sudden changes in the source magnitudes or sources, or sudden changes in the circuit elements. In the circuit elements, provided the system should consist the energy storage elements like inductor, or capacitors. So these are the reasons behind the production of the transients in a system. So what are these reasons? Here are sudden changes in the source magnitudes or sources, sudden changes in the circuit elements provided. The system should consist the energy storage elements like inductor or capacitors. Let me take with an example. Let me explain with an example here. Here you see, it is a 100 volt source. Let us take it is 100 volts. Okay. Now it is actually connected to an RL circuit like this. It is RL circuit. So it is connected like this. It is position 1, and this is another source. Here it is 50 volts. Okay. So if I change this switch, from position 1 to position 2, if I change this switch from position 1 to position 2 at t is equal to 0, then there will exist the transients in the system. That means there is a change in source voltage suddenly from 100 volts to 50 volts, change in source voltage, provided the system should consist the energy storage elements like inductor or capacitor. Here the inductor is present so that the transients will exist. If there is no inductor, that means if it is having only the resistors, this is one resistor and it is also another resistor, then there will not be any transients even if you change or if you shift this switch from position 1 to position 2. So that is what we need to understand here. The reasons behind the production of the transients are sudden changes in the source magnitudes or sudden changes in the circuit elements. Now let me explain these sudden changes in the circuit elements. Now take this another example. Here it is 100 volts source. 100 volt source. Here it is the resistance, and here it is another resistance which was controlled by a switch, and this is an RL circuit here. So this switch, it is 100 volts. Let us take it is 20 ohms. It is also 20 ohms. It is 20 Henry. Let us assume it's only an example. So if we change, that means the switch is on, switch is off. Switch is off means switch is in open position. Switch is in closed position means switch is on. Whenever if you suddenly switch on the supply, if you suddenly switch on this switch, that means if you contact this one with this one, there will be the production of the transients here, because there is a change in circuit elements. Previously before switching on this one, only this 20 ohms is in series with this 20 ohms. These three are connected in series. Now whenever we switch on this one, what happens? These two are connected in parallel. So that means there is a sudden change in circuit elements, so that there will be the production of the transients here. So these are the two reasons because of why the production of the transients will happen. Next, how to analyze the transients. This is the third one. It is an important one. So how to analyze the transients. So in this analysis, mainly what we are going to find here is the current through the inductor L of t and the voltage across the capacitor Vc of t. These two are mainly we are focusing in the analyzation of this transients concept. So how to analyze or how to find these things? So to understand this concept, we required some basics here. Those basics are, what are the initial and final conditions? Initial conditions and final conditions. Initial conditions and final conditions. So we need to understand these initial conditions and final conditions for the inductors and capacitors. So to understand these initial conditions and final conditions, so let me take an inductor here. First, let me write for an inductor. It is a switch. This is an inductor, and we are applying some supply here, V of t. Whenever the switch is on, t is equal to 0, the current will circulate through this, and this is an inductor. The current will circulate through this. Let us take that current is L of t. Because of the current flowing through this inductor, there will be the production of this voltage, that is VL of t. This is VL of t. Okay, now see here, VL of t. VL of t is equal to, we know this information, that is L into dIL of t by dt. Voltage across the inductance offered by this inductance, IL of t, current flowing through this inductance. Now you see, let me take the time axis here. It is t is equal to 0, at which the switching action is done. T is equal to 0 minus, just before the switching action is done. T is equal to 0 plus, just after the switching action is done. Here, if we switch on this supply here, if we switch on this supply, I am going to concentrate, you see here, I am going to concentrate this duration, 0 minus to 0 plus. Within this short duration, what is the change in this current? So almost this duration is 0 plus to 0 minus, 0 minus to 0 plus, this duration is 0. Almost it is 0. If the denominator of this part is 0, then what is this? This is infinity. So this one is infinity. This is infinity, means VL of t is infinity, means VL of t is nothing but this V of t. That means it requires infinity amount of voltage to change the current within this short duration of time. It requires infinity amount of voltage to change this current within this short duration of time, which is not practically possible. Infinity amount of voltage is not possible practically. So what happens? There will not be any change in this current flowing through the inductor. That means the inductor, whatever the current that is flowing at t is equal to 0 minus, the same current will flow at t is equal to 0 plus also, because of this reason. That means what I can say here is, this is an important point, IL of 0 minus is equal to IL of 0 plus. That means whatever the current that is flowing just before the switching action is done, just after the switching action is also, the same current will flow through the inductor. This means the inductor, this is an important point, the inductor doesn't allow sudden changes in the current. Sudden changes in the current. Suddenly, that means within this short duration of time, there will not be any changes in the currents that is flowing through the inductor. This point is important. Now you see, previously, that means before the switching action is done, this inductor is not at all connected to this voltage. So the current, that means the switch is in open position. That means there is no current flowing through this inductor at t is equal to 0 minus. Means at t is equal to 0 only the switch is on. At t is equal to 0 minus the switch is in open position, so that no current will flow through the inductor. So IL of 0 minus is equal to IL of 0 plus, we know that is equal to 0 amperes actually. But in some cases, some of the current will flow through the inductor. So in those cases, that means some of the current, suppose this is an inductor, this was connected to a supply. Okay, this is a switch. Okay, it is some voltage 100 volts, and here the switch is connected to some 50 volts or like that, and this is position 1 and this is position 2. It is 100 volts. Suddenly the switch is moved from position 1 to position 2. It is position 2 at t is equal to 0. Previously, before switching action is done, that means at t is equal to 0 minus, before switching action is done, let us take the current flowing through this inductor is, it is some I naught current is flowing. That means IL of 0 minus is equal to I naught. Even though we shifted this switch from position 1 to position 2, according to this point, there will not be any change in the current because of the switching action. That is, IL of 0 minus is equal to IL of 0 plus, that is equal to, here it is I naught. Initially some current will flow through that. So finally, if you want to represent this inductor at t is equal to 0 plus, at t is equal to 0 minus, if the inductor is, this is an inductor, let us take, at t is equal to 0 minus, this is the representation of t is equal to 0 minus, this is the representation of an inductor. Now at t is equal to 0 plus, the inductor can be represented as like this. Anyway, the switch is on at t is equal to 0 plus, so this is switch is closed here, the switch is closed, and then this was, I can draw this circuit as like this. It is I naught. At t is equal to 0 plus, this is I naught. This is how we can represent the inductance at t is equal to 0 plus. Now, this is the initial, so this means it is the initial conditions. Initial conditions means this inductor doesn't allow the sudden changes in the current. So initial part of this, initial part after the switching action is done, that is initial conditions, that is IL of 0 minus is equal to IL of 0 plus is equal to I naught. Okay, if there is any initial current I naught, then we can represent like this. But here there is no initial current here, so I naught can be 0 amperes here. I can replace with 0 amperes. I naught is equal to 0 amperes. Now that is about the initial conditions. And also VL of t is equal to L into dL of t by dt. So let me write another equations here. VL of t is equal to L into dIL of t by dt. Now dIL of t is equal to dL of t by dt is equal to 1 by L into VL of t. So integrate on both sides of this equation. IL of t is equal to 1 by L. L is independent of the time, so I can take it out from the integration. So VL of t dt. Now let us consider this switching action, this time scale here. T is equal to 0 minus 0 plus, it is tau, it is 5 tau, it is infinity, it is minus infinity. It is equal to 0 is the switching action normally we are taking. Now I need to find the current flowing through the inductor. I need to find the current flowing through the inductor. T is equal to 0 minus 0, switching action. I need to find the current flowing through the inductor at some time t. That t may be from 0 to t, 0 to infinity, any time. 5 seconds, 20 seconds, 30 seconds. I need to find the current flowing through the inductor. So for that, I am finding this expression here. L of t is equal to 1 by L into integral VL of t dt. So these limits, what limits I need to consider here is, it is having the initial conditions also. Initial conditions means from minus infinity to 0, it is having some current. Let us take at t is equal to 0 minus, the current flowing through the inductor is I naught amperes. Okay, from minus infinity to 0 minus, it is having the current as I naught amperes, initial current. That means so this that means here I need to find the current at some time t here. So I am going to write these limits here, that is from minus infinity to t. I need to consider these initial conditions also, so that I am taking the limits as minus infinity to some time t here. So this integration I am going to split here. It is 1 minus infinity to 0 VL of t dt plus it is 1 by L into integral 0 to t VL of t dt. I can split the integration like this. So this current, the current from minus infinity to 0, initial current, that is I naught. I am taking this one as I naught, and this current is, write it as it is, VL of t dt. So it is IL of t. So for t greater than 0, that means 0 to some infinity, any time, at any time, if you want to find the current flowing through the inductor, then how to draw the circuit here is, this is the circuit that we need to draw. So here it is I naught. It is I naught. So this is IL of t. This current is flowing like this. So this current IL of t is equal to I naught plus this current. So this is how we need to represent the inductor for t greater than 0. Now at t is equal to infinity, that means under steady state condition, there is a suppose I am applying the DC supply here, it is L, t is equal to 0, I switch on the supply, it is a DC supply, some many volts, 100 volts, and this inductive reactance XL is equal to 2 pi FL, we know that. What is the frequency of DC supply here is F is equal to 0. If F is equal to 0 for a DC supply, XL is equal to 0 ohms. If I substitute here, XL is equal to 0 ohms, it will act as a short circuit. That means under steady state condition, or steady state means final condition, that means at t is equal to infinity. Under steady state condition, this inductor will act as a short circuit. So this is the circuit that we can draw at t is equal to infinity. So finally, what I want to say here is a representation of this inductor at t is equal to 0 minus, at t is equal to 0 plus, and at t is equal to infinity, and at t for t greater than 0. So these four are important for analyzing the transient analysis. So right here it is at t is equal to 0 minus, at t is equal to 0 plus, at t is equal to infinity, and for t greater than 0 the inductance, here it is the inductance, representation of the inductances here. At t is equal to 0 minus, this is the inductance representation. At t is equal to 0 plus, just now I explained, this will act as a open circuit, and whatever the current initially that is flowing, I need to represent this current here, it is I0. At t is equal to infinity, this inductor will act as a short circuit, this inductor will act as a short circuit. And for t greater than 0, just now I explained this, so for t greater than 0, this inductor will act as, I can represent this inductance like this. So this is I0, this is I of t. Okay, so these four representation of this inductance or inductor is important for solving the problems. Okay, t is equal to 0 plus, infinity for t greater than 0. This is the procedure for that. Next, this is about the inductance. Next, coming to this representation of this capacitance, representation of the capacitance here. Let us take a capacitor here, same thing, instead of inductor I am taking the capacitor here, capacitor. Same time axis, t is equal to 0, 0 minus, 0 plus, tau, 5 tau, it is infinity, it is minus infinity. This t is equal to 0 is the instant at which the switching action is done. T is equal to 0 is the switching action instant, and C is the capacitance offered by this capacitor, and we are applying some supply here. That supply here is some voltage, it is suppose it is V of t, or some voltage here, and whenever I am applying some voltage, and if you switch on the supply, some current will circulate through this capacitance, that is IC of t, and the voltage across this capacitance is nothing but VC of t. The equation I can write the equation for the capacitance like this: IC of t is equal to C into dVc of t by dt. My intention here is from here to here, 0 minus to 0 plus. Within this short duration time, if I want to get the change in the voltage across the capacitance, then the current that I need to send through the capacitance is infinity, because dt is approximately 0. Whenever it is 0 in the denominator, then this value is infinity. Infinity amount of current I need to send to get the change in the voltage across the capacitance during the short duration time, dt equal to 0. So practically it is not possible, so that we are not getting any change in this voltage within this short duration time. That means the voltage instantaneously, the voltage cannot be changes. That means the capacitor doesn't allow the sudden changes in voltages. Inductor doesn't allow the sudden changes in current. Similarly, the capacitor doesn't allow the sudden changes in voltages. That means the capacitor doesn't allow the sudden changes in the voltages. That means whatever the voltage that is present at t is equal to 0 minus, The same voltage will be present at t is equal to 0 plus also. That means Vc of 0 minus is equal to Vc of 0 plus. So this is an important concept, similar to that of inductance. And another point here is another thing. Here t is equal to 0 minus, the switch is in open position, so that the supply is not connected to this capacitance. So there is no voltage initially, so here this value is 0. Vc of 0 minus is 0, so that Vc of 0 plus is equal to Vc of 0 minus is equal to 0 volts. Sometimes the capacitor will have the initial voltage. At the time, this Vc of 0 minus is equal to Vc of 0 plus is equal to that initial voltage I am assuming as V0 volts, similar to that of I0 in case of inductor. Here it is V0 volts. So this is what we need to find. Next, IC of t is equal to, what is this? IC of t is equal to C into dVc of t by dt. I can write this dVc of t by dt is equal to 1 by C into IC of t dt, IC of t. And if I want to find this Vc of t is equal to, if I apply the integration on both sides, then I will get 1 by C integral IC of t dt. Here to find these limits here, similar to that of for that inductance case, I need to consider from minus infinity to some time t, minus infinity to some time t. I need to consider the initial conditions also here. So it is 1 by C, if I split this integration minus infinity to 0 IC of t dt plus 1 by C into integral 0 to t IC of t dt. And this minus infinity to 0, that means before the switching action is done, if there is any voltage across the capacitance, that is V0, initial voltage V0, and this is 1 by C integral 0 to t IC of t dt. It is Vc of t. And this capacitance, we can represent, so this is Vc of t is equal to, this is the equation, V0 plus 1 by C into integral 0 to t IC of t dt. This capacitance for t greater than 0, I can represent this capacitance as, it is initial voltage V0. What are the capacitance? Same here, it is capacitance here, capacitor with the initial voltage plus or minus V0, and this is capacitance. I need to place here capacitance. So here it is plus and minus V0. So it is Vc of t, and this is this voltage will be across this voltage. Okay. So Vc of t is equal to V0 plus this voltage. So for t greater than 0, I can represent the capacitance circuit like this. And also for a DC supply, if I apply the DC supply for the capacitance under final condition, it is C value. Now XC is equal to, value of XC is equal to 1 by 2 pi FC. This is the formula for finding the capacitive reactance. For a DC supply, F is equal to 0. If F is equal to 0, XC is equal to 1 by something, 1 by 0 is equal to infinity. XC is equal to infinity means this will act as a open circuit. That means at t is equal to infinity, under steady state condition, this capacitor will act as open circuit. So these 4 points are required for analysis of these transients of a systems. So let me represent in one all the 4 things in one notation here. That is, at t is equal to 0, at t is equal to 0 minus, at t is equal to 0 plus, at t is equal to infinity for t greater than 0. How will be the circuits here? How will be the capacitor representation of these capacitors? T is equal to 0 minus, this will be the capacitance, and the initial voltage is V0 is the initial voltage at t is equal to 0 minus. Now at t is equal to 0 plus, so it is the switching action. 0 minus, 0 plus is tau, it is 5 tau, it is infinity, it is minus infinity. It is the switching action. At t is equal to 0 minus, the switch is in off position. At t is equal to 0, the switch was closed here. At t is equal to 0 plus, the switch was closed here, and this capacitance will act as like this. Initial voltage, I need to represent the initial voltage V0, and it will act as short circuit. This capacitor will act as a short circuit here at t is equal to 0 plus. Now at t is equal to infinity, this capacitor will act as open circuit. And for t greater than 0, we already proved that for t greater than 0, this is the case for t greater than 0. This is the voltage. So this capacitance I can write as, this is the voltage, and here it is the capacitance for t greater than 0. So this is the initial voltage, it is Vc of t. Okay. So this is about representation of the capacitances at different instants, that is at t is equal to 0 minus, 0 plus, infinity for t greater than 0. So a representation of these inductances, capacitances at different instants is very, very important for analysis of the transients. So these are the very basics, that means initial conditions and final conditions. So these two comes under initial conditions, this will comes under final condition. It is in between initial and final condition, right? If there are any resistors, at t is equal to 0 minus, if there is a switch here, this is a resistance, and the current that is flowing through this is, let us take it as IR of t, and the voltage that you are applying here is, it is V of t, and the voltage from here to here is VR of t. So it is t is equal to 0 minus. At t is equal to 0 plus also, I can represent there is no change in the resistance values. Same current IR of t, it is plus or minus VR of t. At t is equal to infinity, there is no change. At for t greater than 0, there is no change in its resistance. So as it is, we can write this resistance value. Okay, this resistance is here. Representation of the resistance is as it is for t is equal to 0 minus, at t is equal to 0 plus, t is equal to infinity for t greater than 0. Only what we need to remember here is, in the case of inductance and capacitances, representation of the inductances, capacitances at different instants. Okay, with this session I will stop here. Next class I will explain the problems on these concepts.